Hey guys, this is Terrence, and welcome to the new episode of RhinoPython and GhPython Playground. And this is today's pattern. It's basically a Pentagon growth pattern. So the logic of this pattern is we create a baseline or base pentagon. The system or the program, the program will help us generate more polygons based on the existing ones, and the whole pattern will keep growing out. And when we have the pentagon growth pattern, we can do some geometry manipulation to convert the polygon into these 3D geometries. So here is the whole process of generating this pattern. There are two essential functions here. The first function helps us to generate the pentagon based on the available edges. That means if we provide an edge here, we first use this function. It's a matrix. This is a linear algebra function. Helps us to find a new point from the existing line, with the angle we provided. So we will have this new edge here, and the angle between these two lines are 72 degrees because it's a pentagon. So when we have this new edge, we just need to move this edge to here. So we have two edges of a pentagon. Then we replace this newly generated edge with the previous one and use this edge, repeat the same step to create the next edge, and we just repeat this process, we can get a pentagon. And then if we want to keep generating the new polygon, keep generating new pentagon, we need to place all the newly generated edges into a list. Then we can randomly select an edge from that list to generate new pentagons, just like this. And maybe this will be a new future edge, and new pentagon will be created here. But there's one more thing we need to do here, that when we select this edge and generate this polygon, we need to remove this edge from the available edge list, because we cannot generate new polygons from this edge. It's already been used. So this is first function. We generate we do the pentagon growth. The second function helps us to avoid intersection and containment happening in the generating process. Here are two conditions we need to avoid, because we don't want to just generate the regular pentagon. We still want our point to move away from its original position to make the whole pattern looks abnormal. So there will be two unexpected or unwilling situations. The first one is called containment, that some polygon is completely inside the existing ones. Another condition is called intersection, that a new polygon intersects with the existing one. So these are two things we need to avoid. And my solution is first to shorten this newly generated polygon, because you can see in the original ones, these two polygons are attached and these two are attached. So when we start to detect intersection, these two polygons are intersect with each other, and if we don't detach this one from its mother one or its base one, every time the program will return the intersection information, and then we will never generate a polygon. So this is what I do. I shorten the polyline, then create a new polygon. And in this condition, this newly generated polygon is detached from its mother one. Then we can use this newly generated smaller and detached polygon to check the possible containment, possible inclusion, and the possible intersection. And I think these are two major functions we need to use in our today's pattern. And let's start hands-on this pattern, hands-on this episode's geometry. So okay, I should bring up this one. This is our script here. And the first thing is I want to create an initial line. So I should bring it here. So I just say line here, make it bigger, and I can just define a line somewhere here. Just make it random. And I hope this one will be more clear. So I will change it to Arctic mode. And yeah, this is our baseline. We will first use this baseline to generate a pentagon. So we need to create a GhPython node. Change the input of X to line, and switch the type of input to line. Maybe remove this input for now, and I will choose show code input parameter, and the input is path. Then I should connect this line to here and create a file path node. Make it synchronized and select one existing file, which is the script file here. Okay, so connect to the code end. And let's just check if this function, if these two files successfully connected. Let me just bring it to here. And first I want to import rhino.geometry. I will use this library to do our today's pattern. Import rhino.geometry as RG and then print test. Save it to see, okay, it works. Then we can start working on our codes and functions. And before that, I still want to import a random library because we will use this library a lot in our today's playground. Import random. Yeah, I think I could say from random import everything. Then I will set the seed as maybe 300. I can actually create a new input here as seed. I just call it rseed to avoid the syntax name collision. And this should be an integer. I will set it 300 here. Then I can just replace this number with our new variable rseed. Save it. Yes, I think it works. Then let me see what we should do first. First we should which one? Oh, this one. First we should write function to generate this pentagon. So we can do we can define a new function called generate pentagon. Generate penta is enough, and we should input a line, which is our baseline. But here I want to just put a pass here because I want to initialize two important lists, or yeah, I want to initialize a list and a set. The list is for the pentagons and the set is for the edges. Edges, just I mentioned, edges was used to generate the future pentagon. So I want to say available edges equals a list, and I can put the line, the current line into this set. And the second list I want to create is pentagons. It should be an empty list because we don't have any pentagons here. So I think we can start working on this function. I want to say step 1, generating pentagon. Pentagon, yeah. And inside here, first let me see. inside here, first we need to define, we need to find 2 points, the start point and end point of this line. So I want to say original point equals to line dot from and line dot to. These two are line properties. These two are line properties belongs to this Rhino geometry library, and this one gets the from or the start point of the line, and this one get the end point of the line we provided. And then we will need a new list to contain all the new points, because Pentagon has 5 points, right? But actually, we already have 2 points here. We just need to generate 3 other 3 points. So I think that's enough. So maybe we generate 3 points and we use 2 of our current points. We put 5 points together to generate a new pentagon. So first of all, I will put the start point into the pentagon point list. The first point should be 2 because we start pentagon from here instead of here. Here is line dot from, here's line dot to, and we are going to grow in this direction, in this way, yeah. So, and then we can start generating the pentagon. But here I want to add another variable called iteration, because I will use a while loop to repeat this process. And yeah, we just use a current line, generate a new line, generate a new point by this function, and we will updating the newly generated line with the previous line, and keep generating new points. Sorry. So I will use while loop here, and while iteration is smaller than 3 because we just need to generate 3 new points. And inside here, we need first find the vector, the direction of the existing line. So we will use the function called point3d.subtract, and use the line to minus line from point. Then we will get a vector in this way. The next step is our angle, the angle of the corner angle of pentagon is 72 degrees, but if we want to use cosine and sine function, we should first convert it into radians instead of degrees. So we need to have a radians value here called radians 72, but I also should import I should import radians here along with cosine and sine. So why don't I just import the math library from math, import everything. So we will have a radians value. Then we can just calculate the x position and y position, x coordinate and y coordinate of the new point. So I name it as next x equals to vector 0 multiplied by cosine radians minus vector 1 multiplied by sine radians, and we do the matrix transformation on y-axis or y-coordinates. We can do vector 0 multiplied by sine radians and plus vector 1 multiplied by cosine radians. And I should keep the space. I should keep the I should keep the format uniform or consistent. I should keep the format consistent. Then next thing is we have our new coordinate. we should move this point to here. So we just need to add this coordinate by the end point. So what we need to do is new point equals to we just because we have this x coordinate and y coordinate, the first thing is to create a new point. So we say new point equals to rg dot point 3D next x next y and 0, because now we're just working on plan. We are not working on the 3D space, so we just keep the z as 0. Then we can just working on the xy plane. Then we can create a new line by create a new point. No, now we need to move that point instead of create new point. We just move that point by using the plus. I mean, we will do new point plus equals to line dot 2, which is end point. Then we will have a new point. Then the next thing is we need to replace the newly generated line with the previous line. Then we can keep working on the next points. So we should do new line equals to rg dot line with the line 2, and another end of the line is new point. And we replace the line with a newly generated line, and we will also append the newly generated point to this Pentagon corner list. So we should say I want to make it more clear. These are points instead of edges. So Pentagon PTS dot append new Pentagon PTS dot append. Which point I should append? Yeah, I should append this one, this line dot 2, because we already updated this line. Line dot 2 is the end point of the newly generated line, and which is also the new point we generated. And then we need to update the iteration value, or the while loop will never stop. Then at last, because we already append this point into the Pentagon point list, when we create 1, 2, 3 new points, we still need to append this new point, this start point of the baseline into our point list. So we should do penta pts dot append original PTS with index of 0. Then we can just return the Pentagon, penta PTS, and I hope this works here. So let's test it out. We can just say a equals to generate Pentagon line here. Yeah, so save it and see. Okay, it's actually going zoom or yeah, it's actually sorry. Yeah, it's so hard to manipulate this thing. Yeah, it's actually going this way. Start from here, going to here, then here, 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 and this one. So I will use the polyline node to visualize this polygon. Yeah, so this is the polygon we generated, and with this logic, I think now we can keep generating the new polygon based, new pentagon based on the existing one. But another thing I want to do is I want to add all of newly generated edges to this available edges set. So I might need to create another function called add define add edges. We need a pentagon points that was the point we newly generated, and this one, this available edges, and I want to comment we want to add a comment above this function to make things clear. I'd like to say step 2, adding edges to the edge set. And inside here, I need to loop over all these 5 points and keep adding new edges. Oh, I think these 4 edges are the newly generated edges. I just need to add these 4 edges into the available edges list. So I just say for I in range length penta PTS and make PTA as the new start point of the available edge. Penta PTS index of 0 and PTB equals to penta PTS I with index I plus 1 and modulo by length of penta PTS. Then we will have our new edge. Use the Rhino.geometry library, rg.line, and with start point PTA and end point PTB, and then we add this new edge to the available edge set. edges.add new edge. So we have this one. Oh, sorry. So I think here we can also do the function called add edges to test is this function working well. So we do add edges. We need to put A as the first parameter, and we do these available edges as second parameter. edges and save it. Okay, I prefer to print it out to see how many edges we already added to here. Print, save it, and none, and it's not right here. Let me see how can I fix this. Edges, add edges. ADDEDGES length pentagon PTS. Did I create the new line here? Print new edge, save it. Yes, I have new edges here, but here shouldn't be empty. Yeah, let me replace this variable edge sets. Let me change the variable name of this one. I hope it's not working. And oh yeah, I know why, because this function returns nothing. Why I make this kind of stupid mistakes? I just need to print the available edge set, and I will get all the lines inside here. And you can see these are all of the available lines. Then we can do a while loop outside these 2 functions, and we can start making the Pentagon growth based on the iteration we provided. So we can do, let's first set current iteration as 0, and while current iteration is smaller than, let's just set it to make it very small and to test it out. And later we can just replace this value with a larger number, then we can have a higher iteration. So inside here, I prefer to first update the iteration value, because I'm afraid I will forget this and make the whole program stuck in the infinite loop. And then I will randomly choose an edge from the available edges list. So I will do random edge equals to did I import random here? Yeah, I should do choice list and available edges. Then I will have a random edge. With this edge, I will create a new pentagon. But here I want to mention there's one thing we need to care about. We need to really care about. Now think about if we generate a pentagon. How to say that? Yeah. Now, just assuming that we generate a pentagon clockwise, right? So here is the first point, second point, third point, fourth point, and yeah, go back to the fifth one. In this condition, we do it clockwisely, but if we select this edge as available edge, the edge of this polygon, then the line's direction is going from here to here. If we keep using this line to generate a new polygon or new pentagon, that will still make the new point goes in this direction, then created a an overlapped pentagon on its original one. So in this condition, we should flip this line, make this line going reversely, then we can create a new pentagon based on the selected edge. So I'd like to say random edge dot flip. We just flip this edge, then we will have our new pentagon equals to generate pentagon, and with the random edge, with a randomly chosen edge, then I think we have our pentagon. We need to append this pentagon to the pentagons list. So we should do pentagons dot append new penta, and at the same time we still need to add all these newly generated edges to the available edge set. So we can say add edges with a new pentagon and also available edges set. Then we can just remove the current edge from the available edges set. edgs dot remove, I think, rand edge, and here is a complete while loop, and save it. Let me see how it goes. We have this, and yeah, oh sorry, where is our polyline? Zoom. Oh yeah, we have our first one here, and maybe let me increase the iteration. See what I will have. I have only 5 points, is that right? No, it's not right. Oh sorry, I just forget to replace the output A with the to assign these pentagons to the output A, and I think we should remove all these two lines of code, and we can do A equals to pentagons. Save it. See what's going on here. And this is now basically RhinoPython list. Let's convert this list into the Grasshopper tree structure. So we do import what GhPython lib dot tree helpers as th, and then we can just do like th dot list to tree. Oh sorry, it's blocked, and save it. Then we have these kind of things. Let's do the polyline again, and see we have this these newly generated generated pentagons, and I can also make it closed by doing sorry, it's not this one. It's called toggle, Boolean toggle. Here, now we have this. We have these 4 newly generated pentagon, and I think here I can also add a new input called iteration max iteration, and I prefer to set it as 5 for now. I don't want to make it too big, and a smaller number will be helpful for us to testing our functions. When all of our function going very well, we can just increase the number. And here I can replace this 4 with max iter and save it. Now let's change this value to see how it works. It's functioning pretty well, and the situation appears that is intersection. But before addressing this problem, I want to write another function to move each of the point to make the whole pattern looks a little out of normality. So here I want to add another function. Let's say step 3, moving points. And here I can say the function name is move PTS, and we put the Pentagon PTS into this function. I will make it more spacious, and then let's see. Inside here, I want to first create a copy of the current pentagon of the newly generated pentagon point list, because I don't want all the codes inside here affects the original pentagon list. So I'd like to say new PTS equals to Pentagon PTS. Here, this is make a copy of the Pentagon point list. Then we can do for I in range. Start from 1 and end at length of Pentagon PTS -1. Maybe I can do it later. I can do this later. I can just say length Penta PTS. I can just directly put the length of pentagons into the range, and you will see what's the problem of doing this. And we can just say PT equals to Penta PTS at index of I. Then we need to find the X offset value equals to uniform. This is a random function, -0.7 to 0.7 maybe, and I will copy and paste this X off, and I will modify it to Y off here, still -0.7 to 0.7. But for the Z offset, I want to make it bigger. I want it ranges from -1 to +3. And then updating the position of new points. I equals to rg dot point 3D, and with 3 coordinate 0.0 plus X offset 0.1 plus Y offset and 0.2 plus Z offset, and we have our new points. We have all of our points updated. Then we just return this new PTS list, and we can update our points in our while loop by calling this move point function. We can do new penta equals to move PTS new penta Save it, and yeah, something goes wrong here. Sorry, new penta. Save it, and yeah. So why it's so moves so quick? So you can see there is something unwilling happened, which is in our design, these two lines should be these two pentagons should share the same line here. That means these 2 points shouldn't be moved. But now, because we loop over all the newly generated points and we updated the position of all the points, these 2 original position are also updated, that then it shifts from its original position, which is something we want to avoid. So what we want to do is when we are updating the point, we will need to avoid touching the first point and the last point. So what we need to do here is just inside this loop in the move point function, we start from 1 and ends at the last second point in the list. Then save it. We will have all the points, all the polygons connected like this. And now I think it's time to address the intersection and containment things. That's one of the biggest challenge in today's pattern. So maybe we need to define a new function here. It's our 4th step. We can say step 4. Checking intersection and inclusion. Yeah. So we can define a new function. We can call it check intersection, and we put 2 pentagons, pentagon A and pentagon B, to check is are these 2 pentagons included with each other, or they intersect with each other. Then I can do, yeah. So let me just pass this one and make the points invisible and just show these polygons. And I hope in this way I will make the whole process more clear. Maybe decrease the iteration or change the random seed. Yeah, we will have another pattern here. And inside this check intersection function, what we need to do first is to flatten all of the pentagons, all of these newly generated polygons, because you see these polygons are not coplanar. If the polyline or polygon are not coplanar, we have no way to check their intersection. So the first thing we can set all the points, all the corner points z-axis as 0. So we flatten all of the polygon to the 2D, all of the 3D polygon to the 2D polygon on our XY plane. So we can do plan pentagon A equals to a list comprehension called rg.point3d pt0 pt1, and the z coordinate should be 0 for pt in pentagon A, and we do the similar thing on pentagon B equals to rg.point3d. I can just copy paste, but yeah, it's fine. pt0, pt1, and 0 for pt in pentagon B, and we have 2 flattened pentagons. Then the next thing is, as I mentioned at the beginning, I will shorten this newly generated polyline to make it detached from its mother or its base polyline, its mother or its base pentagon or its base polyline. So I can say temporary pentagon A equals to rg dot polyline curve. because now they are stored as points instead of polylines. So I want to first convert it to curves. Convert it to polyline curve, then make it short, then close it to create new detached pentagon. So I will do temp A equals to rg.polyline curve. Let's place our p penta A into here, but I want to make a note here. That is, pentagon A should be new pentagon. Then pentagon B is one of the existing one. And then I can just calculate the dimension of the newly generated polyline. I can say dom equals to temp A dot domain. Then we can get the domain of this polyline curve. The next thing is update this temp A polyline curve by doing temp A dot trim with the start domain plus 0.1 and the end domain minus 0.1. Make it short in the beginning and in the end. Then we can do p pentagon. What we should do, p pentagon is to temp A polyline curve temp B. Oh yeah. Then we can just update the pentagon, p pentagon start point and end point to the. Let me bring up this again. When we have this, we can just update the, how to say this? Yeah, I think we can just replace the start point and end point of the original pentagon with the start point and the end point of the newly generated pentagon. Of the temp pentagon, sorry. Let me say it again. So the next thing after we have this temp A, we just replace the start point and end point of newly generated pentagon with newly generated polyline curve with the temporary start point and temporary end point. And in this way, we can make the polyline curve short and detached from its base 1. So we can do p pentagon. The first point equals to temp A dot point at start. And we do the same thing at the end point of the newly generated pentagon. Minus 1 equals to temp A dot point at end. And yeah, and we just updated this pentagon. Then we can make them closed. So we just say polyline A equals to rg dot polyline curve. Let me see. The first one, for this one, we should put this p. This should be p penta A, plan pentagon A. Yeah, p penta A. If we want to make it closed, we need to add the start point of the start point of the polyline into the end of the list. Then we can make the start point and end point corresponded to make the whole polyline closed. So we should add this pentagon A point list with p penta A with index of 0, which is the start point. And we do the same thing on polyline B. Polyline curve p penta B plus p penta B 0, the same thing here. And then we can start check their relationship. The function we need to use is called rg.curve dot planar closed curve relationship. and we need to input. Let's check. We need to have curve A, curve B, test plan, and tolerance. Oh yeah, we still need a plan here. So I can say plan equals to rg.plan.word xy, and we will get a word xy plan for testing. Then we have poly A, poly B, and poly A, poly B, and plan, and the tolerance I just put 0.1 here, save it, and hope everything's going on very well. Then we just need to return. Let me first check the value type of the value, what kind of value this function returns. So maybe we can go to the Rhino geometry library to check this one, curve. Let's go to the curve methods, and I think there will be an planar closed curve relationship. Let's say relationship. Yeah, this one. Click it and you will see it returns region containment. This is another class in Rhino geometry library that includes 4 kinds of variables, 4 kinds of values. They are disjoint, which is what we want, and the mutual intersection, which is 2 polyline or 2 polygon intersect with each other. There's A inside B, that means polygon A is inside polygon B, and yeah, vice versa. So basically, we just need, we just hope these two polylines or these two polygons are disjoint. If it's not disjoint, we return maybe we return a true value. That means these two polygons are intersect or they are contained in each other. So here we should say, just keep this in mind, keep this region containment class with these 4 values, keep this in mind, then we will implement this in our code. So when we get this relationship, we just need to return relationship is not equals to rg dot region containment dot disjoint. This means if this if the relationship between these 2 pentagons are not disjoint, we return a true. That means they are intersecting or they are containing each other. If it is disjoint, this will return a false. That means when we check the intersection, there's no intersection or inclusion happen. So we have this function. We can implement this function inside here. And let's say, how can we implement it here? We can just say is COLIDE is collide equals to false. And then we loop over all of the polygons all of the pentagons in the pentagon list to check the newly generated pentagon with each of our existing polygon. So we can say for penta in pentagons, and let intersect let intersect equals to check intersection. And this is the function of intersection, yeah. And we use the new pentagon as PENT, use the new pentagon as first input, and the penta, which is one of the existing pentagon, as the second input. If intersect happened, and we set is collide as true. And then after the loop, we can say if is collide, if is collide variable is true, we can just say if is collide, then we can continue. That means if we detect the collision, we just finish the current loop and goes to the next one. So we will not append the Pentagon and then those edges to the Pentagon list and available edge set. So I think, yeah, this is our function. Let's save it. Yeah, you can see then the intersection disappeared. And I think this time we can try to increase the iteration, to increase the max iteration to check if everything is functioning very well. So I prefer to save these things to avoid some unexpected errors. And I want to create a slider with a larger value, maybe 100. I hope this one will not crash. Okay. And let's see, we have our growth. We have our growth pattern. If I reduce this, if I increase this, and let's switch to the top view, we will see none of the polygons, none of the pentagons intersect with each other or included in another one. So we have this one. And I think we have all the patterns. We have our patterns. Then we can use our pattern to generate the geometry, generate this kind of, where is the image? Generate this kind of umbrella geometry. But I don't want to use code here. I can just use Grasshopper nodes. That will be easier for us to create this pattern, these geometries. So what I will do is first, we have this one. This is our top. This is our top polygon. We need to create a projected polygons. We need to create projected polygons. So we can say project. Sorry, let me move it to here and make the Grasshopper window larger. We can do project here and make xy plane projections. Then I should make it smaller. I will scale them according to their centroid. So I will say area and the scale. Put these geometries into the scale node, and here is the centroid here, and factor. Maybe I will make it pretty small, so I will scale it by 0.2 and make this invisible. So we have this base one. And the next thing is we still need to create an intermediate one. So maybe we can just move this thing, we can just move these polygons, these base polygons up above, move these polygons above a little bit, but I don't know, do I have the twin? Yeah, I have twin curve function here, so I have twin curve nodes here. That will make our life much easier. I would say this one is the ground. I would like to say these polygons are ground polygons, yeah. And sorry, my English is getting so worse today because I'm still in holidays, so yeah, my brain is still very slow. And yeah, I think we can create intermediate polygon by this way. And here I prefer to put maybe another 0.2 value here. No, it's too close to the it's too close to the top. I will increase the number. Maybe here will be better. And then I need to scale them a little bit to make this intermediate one smaller. Then we will have this kind of umbrella or mushroom shape. So what I want to use is I want to break these polylines by using the explode. And we have some vertices, then we can use the average node to calculate the average center of these vertices. But maybe you can see here is a little shift because there are 2 points at the close position. So maybe I need to use the call index node and remove the index of 0. This is too long. I can just use this one and connect this to here. And yeah, the center point is now shifted back to its average center position. And then we just need to scale these intermediate polylines. We can by using the same node scale, geometry here, centroid here, and factor. This time it could be larger. I have 0.2 here, I have 0.3 here. Maybe this time could be 0.6 or something. And I hope, yeah, this one will create a preferable result. And let me see, we don't need this one. And we have this one, we have this one, we have our top one. We can just loft them to create our pattern. So I will do this one, and this one. I will place 3 of them inside a group. So I will do like I will do merge and create 3 inputs. Simplify each of them and place each of them inside here. This is our top polygon. This is our intermediate polygon, and this is our base polygon. Try to make it nice. And yeah, and invisible all of them. Then we have these 3 lines. These 3 polylines, then we can just use the loft to create this kind of things. Yes, I think we have it. We can just decrease the scale value here to make it looks like umbrella, looks more similar to umbrella. And I can also reduce the scale number of these bases. So let me bake it, and let's see, we have these things. Oh, there's something unexpected that some of these polygons are really close to plan. Some of them are a little above, but some of them are a little below. But that's fine. We can address this problem by changing the seed, the random seed value, or changing some other offset values inside our function. Like this one, we can make it bigger. Maybe we can remove this negative value. That's fine. That's not some big problem. So I think we basically have what we want today. And yeah, this is all of today's content. And yeah, thanks for watching. And if you have any comments, any thoughts, please let me know, and I will try my best to reply each of your concerns. I will also upload this code to the GitHub repository. You will find the link below here. And today is December 30th, so Happy New Year. Yeah, and yeah, that's it. Thank you. Bye bye.